Yeah. Good morning. Anyway, this is the problem that I am going to share with you. Is understanding gravity through the galactic center black hole, Sagittarius A star. The Sagittarius A star is the center of our galaxy, which is coinciding with the dynamical center of the masses. So that is Sagittarius A star. The title itself is quite simple. That is because the problem that I have started is to understand gravity. I mean, it's a very simplest force of nature, but it is very mysterious force of nature. How to understand gravity by using different scales in the universe. And I have chosen the scale of the galactic center black hole because the interest of the galactic center scale, I will come why this is so interesting scale. Let's go. This is the upbeat. See the slide. This one is going down. Yeah. Sure. Right. This plan of my talk is on the shoulders of the giants. I want to display the pioneers who studied gravitation and how to study gravitation by doing experiments or observation. Then I will touch the galactic center black hole and its potential, what we can do with the galactic center black hole. Then about the scale, why this particular scale is interesting for understanding gravitation. Then why to test general relativity and why we need alternatives to general relativity. Then I will touch upon the probes, what are the probes available with us to understand gravity. Then I will talk about classical scalar tensor gravity that has been tested. Then FR scalar on gravity, which is a very serious alternative to general relativity, and testability of the theory near the galactic center black hole. Basically, I will use the probe of the compact stellar orbits that is encircling the black hole at the center of our galaxy. And also I have a focus for upcoming these extremely large telescopes. What we can do with the extremely large telescope like 30-meter telescope or 39-meter telescope that is upcoming, and how we can use these ELTs to test gravity near the galactic center black hole. Then we will see whether we can point out some breaking point of GR near the black hole, so higher dimensions. Is it testable? And then I will, towards the end of my talk, I will touch upon the black hole shadow as a novel probe for understanding space-time or gravity that we have been doing from 1915. This is our old friend gravity. How much we know about gravity? This is a very mysterious question. The first person to try to understand gravity is René Descartes, around 1630s, not Newton. Okay, we all know that Newton was the first person to give a theory of gravity, but we are wrong. If we go back in history, the story goes far back. Descartes was trying to understand planetary motion by proposing that in empty space there are some vortices present. It's called Cartesian vortex. Because of that, the planets are encircling the sun. This is called Descartes' theory of gravity. Then Isaac Newton came, the famous story that apple falls, and that is what gravity is. But Newton's theory of gravity is not the actual understanding of gravity, because that is a phenomenological description of what we see in the sky, the repetition of the planetary orbits and appearance of the comets. And then a person came in 1915 and said, no, what Descartes and Newton said is not the true reality. The true reality is that there is no such vortex, there is no such force. All we have is a geometry of space-time, and space-time is curved, and that is what gravity is. And actually experiments have done near Earth itself. You don't have to go to black holes or neutron stars at the first place to test gravity. You can do it at home. The gravity probe B experiment that I have shown here, the satellite, it has actually measured the amount of curvature near the Earth, and that was published in early 2000s, that Einstein is correct. But is it the end of the story? Is this true, that the general relativity is the ultimate theory of gravity? If it is true, then this is not science, it is like religion. So we are going far beyond Einstein and trying to see why Einstein has been so successful in the last more than 100 years. And the scientific philosophy is that if a theory is successful too much, we have to be worried why it has not been falsified. And that is what my philosophy is in the world. These are the giants. Sir Arthur Eddington was the first person to ask, can we go beyond general relativity? Because he knew the problems of general relativity being inconsistent with quantum mechanics, newly discovered quantum mechanics. Robert Dickey is the central person in my talk because he initiated experimental gravitation in 1960s in Princeton, and he recovered general relativity from the dark age when people thought that no, this is just a mathematical fiction of space-time geometry and it cannot be experimentally testable. But he proved them all wrong and brought general relativity into mainstream astronomy. Then Erwin Shapiro, an Austrian physicist, he devised many experiments to test GR in our solar system. Kip Thorne, we all know, he proposed gravitational wave observatories as a remarkable proof of testing general relativity near black holes. C.M. Will is the leading person now. He started his work in 1970s to test GR in different scales of the universe. And he has a very famous book, Was Einstein Right? All of you can read it, it is a popular book, but you will feel it. And she is the Nobel laureate 2020, Andrea Gage. She won the Nobel Prize for discovering the black hole at the center of our galaxy, and now her team is leading the study of testing GR near the black hole of our galaxy. So what is the potential? Let us see. Potential of this black hole that is sitting at the center of our galaxy. Andrea Gage wrote a paper in 2009, and title of the paper is The Galactic Center, a laboratory for fundamental astrophysics and galactic nuclei. You can see it in the archive number that I have displayed. And this is a unique lab for understanding supermassive black hole and its environs, plus gravity and plus dark matter. In today's talk, I will talk about how supermassive black hole sitting at the center of our galaxy can test gravity. However, we have other potentials. That is part of my other works. I am not going to present that over here. VLT and K, till 2020, they have captured orbits of more than 38 stars. I have written 38 stars within 2400 AU, that means 10 milli/sec, and 1000 AU, which is the orbit of semi-major axis of a very famous star, well-studied star called SO2. That is within 4.8 milli/sec of the black hole. So these orbits have been determined, their semi-major axis, eccentricities and other orbital elements. So it is very easy to use their data to test how gravity is working near the black hole. And recently, Event Horizon Telescope has detected the black hole shadow properly and found that this is a good representation of the hypothesis that the black hole is sitting at the center. And we can use the angular diameter of the black hole shadow to understand how gravity is working near the horizon of the black hole. I should not say too close to the horizon, but at least near 5 times the gravitational radius of the black hole. And this is very surprising that we are now touching almost the horizon. We are going close to 5 times the gravitational radius. Whereas the orbit of the stars is something like 12,500 times the gravitational radius. So this is a large region in the space-time near the black hole that you can probe. Now let us see the potential of the galactic center. First, we can understand the models of the supermassive black hole formation by using the galactic center, because this is our nearest black hole, well-studied black hole. Then we can understand gravitational physics. This is part of my work and my group's work. We can understand extended dark matter distribution, because the standard lambda CDM cosmology demands that there should be dark matter distribution near the supermassive black hole, so we can study dark matter also. Stellar population, very important. These 38 stars is a part of a young cluster near the black hole, and that is very mysterious. How a young cluster containing O-type and P-type stars can survive near the galactic center black hole. Then we have testing space-time metric or the Kerr hypothesis by using the EHT's measurement. This is the spectrum of potential of the galactic center black hole. So now the sourceful precision, the precision of orbits, elliptical orbits, because of relativistic correction that often occurs in case of Mercury's orbit, and that was a testing ground for GR in 1915. one star called SO2. The orbit has been traced by gravity collaboration for more than 2 decades, and in 2020 they published their data, and the short-shield precision of the star SO2 has been detected. That was a remarkable test of GR. Gravitational redshift of light coming from SO2 has also been detected by gravity collaboration. They are using VLT. Their data published 2 years back. And event horizon telescope measurement of the black hole shadow. These 3 measurements in the last 2-3 years have opened a new window to test GR near the black hole. And we are probing space-time from, as I said, 12,500 gravitational radius down to 5 times gravitational radius from the Sagittarius A star. This is remarkable. The scale range is remarkable. So we realized that this is a de facto new era for observational general relativity. De facto means it has been newly realized, and this is really happening. So if Dickey were alive today, he would have been very happy and said, go ahead. Okay? What is the importance of this scale? The mass of the black hole has been precisely measured by UCLA group, Andrea Thesis group, and also the gravity collaboration led by Reinhard Benzel. They won the Nobel Prize. This is a very special scale. Why? Because this, of course, the gravitational radius is okay, fine, 10 microarc second. Perihelion of SO2, 120 AU. 120 AU is something like going beyond the orbit of Kuiper belt. Himadri might be knowing better. 120 AU is going beyond the orbit of Kuiper belt. So that is the perihelion size of SO2's orbit, but that has given us valuable information about how gravity works. So this particular scale is lying between stellar mass black hole or intermediate mass black hole and cosmological scale. So this is a very typical scale that you can test gravity. In stellar mass black hole, stellar scale we have tested because Hulse-Taylor pulsar has tested gravity. In cosmological scale, people are doing work like understanding CMB anisotropy and structure formation to understand how gravity works. But this is a new platform that we can study gravity and say which theory of gravity is correct, and then see whether it is complementary to all other tests. If we calculate the Kretschmann curvature in differential geometry, we can feel the situation. If we calculate Sun-Mercury's system, then the Kretschmann curvature is around 10 to the power minus 22 in the unit. And if we calculate Kretschmann curvature near the black hole by taking SO2's orbit, it's something like 15 order magnitude larger than the curvature of space-time we realize in the solar system. So it is a new platform for us to test gravity. And it has not been strongly tested in this interesting scale. So we have a lot of potential. Now why to test GR? In order to answer this question, I go back to this German philosopher Karl Popper. We all know him. He said long back, a theory has to be falsified. If it is a good theory, it has to be falsified. And general relativity is a theory which has not yet been falsified. This is the irony, and we have to keep our eyes to test repeatedly and say which theory of gravity is correct. Now, the more than 100 years we have come across and it has not been falsified, then what to do? We have to bring the theory into a general framework and parameterize the theory and constrain the parameters from observation and try to rule out all other alternatives. That will be the real test of gravity. And that is what we are doing now. Till now we have tested only in the Whitfield limit of general relativity. Even in 120 AU, if we calculate the curvature, it is not at least of the order of 1. So it is still in the Whitfield regime, but stronger than the solar system regime. What about the Whitfield limit of serious and useful alternatives? That is the question I am asking in my work. So we have to be testing all these alternatives. And why these alternatives required? We have many problems with GR. These are what has been displayed. We have cosmological singularity, if we believe in Einstein's theory. Then we have the problem of dark matter and dark energy. We are not understanding dark matter and dark energy physics because they are based on the assumption that Einstein's GR is correct. Then we have problem of cosmic acceleration. Why the universe is undergoing accelerated expansion? Is it because of negative pressure field, or it is because of breakdown of GR in large scale that is not yet settled down? Then effective theory of quantum gravity. If quantum gravity is there, it should have some approximation, some effective theory in the weak field region, and definitely that should not be zero. Then we have problem of dimensions. Why 4? This is a great problem. Why we have 4 dimensions in the universe. So if we go back to much more open discussions on dimensionality of space-time, then GR is naturally modified, and the question comes whether they are astronomically testable. Now these are our probes: pericenter shift of compact stellar orbits near Sagittarius A star, and angular diameter of the shadow of Sagittarius A star. These 2 probes I will be using in my presentation today. Now first alternative is branch decay theory that was proposed in 1961 by Dickey and his PhD student Branch. This is too technical, so I am trying to explain qualitatively what is branch decay theory. So matter produces a universal scalar field, and scalar field produces a space-time metric. In Einstein's GR, it is simple. Matter produces a space-time metric directly through Einstein's equations. In branch decay theory, it goes via a long route that we have a universal scalar field produced by matter, and that produces the space-time metric. This is what branch decay theory is. Now the problem is that, can we test it? Is it possible to disentangle branch decay theory from general relativity if we calculate the pericenter shift of the compact stellar orbits in branch decay theory near the galactic center black hole? That has been done. The calculation shows that the quadruple moment of the black hole has been taken into account because black hole is naturally rotating, so it has its own non-sphericity. If we take the quadruple moment from very low value to high value and parameterize the pericenter shift and plot it with this spin of the black hole, I consider from very low spin to very high spin and then plot the pericenter shift in micro-arc second per year, we can see that it's very difficult to distinguish branch decay theory from general relativity. The first plot is general relativity region, and these last 3 plots is the difference between branch decay theory and Einstein's GR in pericenter shift of the stars. And you see that it's quite small. It's something like 1 micro-arc second per year. If we parameterize the theory by branch decay parameter, branch decay parameter is the one. If it is too less, it will quantify maximal deviation from GR, and if it is too large, like 40,000 or 1,000 or 50,000, that will be almost like GR. That is what branch decay parameter is. Now if we go back to the very large value of the Dickey parameter that has been given by solar system measurement, we see that the difference between branch decay theory and general relativity is something like 0.003 micro-arc second per year. Doesn't matter what is the spin of the black hole. That says that it is very difficult to distinguish between branch decay theory and general relativity near the galactic center black hole. If we rely on the Dickey parameter that has been given through strong measurement in the solar system. So we need some serious alternatives. And this work was published in 2018 in my own calculation. This is the paper, and I am feeling a bit fulfilled to share with you that this paper got the Nobel citation from Reinhard Genzel in 2019. Okay. And that paper is very influential paper because Genzel's group was trying to identify the scalar field near the galactic center black hole and rule out many models of scalar tensor gravity. So that was some realization that we had. Now let's come to effort, scalar, and gravity. So what is effort gravity? This is the motivation of effort gravity first. In 1970, this model was proposed to explain bouncing universes, oscillating universes. Then in 1980s, Starobinsky proposed that the primordial inflation can be explained by modifying Einstein's equation, simply modify the Ricci function as a general function in the left-hand side of Einstein's equation. And then in 2007 onward, people started working that effort gravity can be a good explanation of the flat rotation curve without introducing dark matter. That was a sensational paper published in Physical Review later by Martin Seleuci and Capoggiello. Then 2014, Capoggiello wrote another paper which explained formation of galaxies and large-scale structures without incorporating dark matter but modifying Einstein's theory of gravity. So astrophysically, effort gravity has been it has been found to be well testable by using cosmology. So what is effort theory? Again, I am not displaying the detailed equation, it is too complicated, but I am trying to explain in a schematic diagram. Einstein's equation get modified on the left hand side due to a function called Fr, analytic functions of Ricci scalar. A scalar field is necessarily coming out, and that is differential of these function with respect to Ricci scalar. If we take a vacuum solution in the weak field regime like Schwarzschild, we will get a metric which is not Schwarzschild, it is called scalar metric. It has a Schwarzschild part, but it has a Yukawa correction coming out. So if we look into the weak field potential, it is something like minus Gm by R. Sin out is the scalar field that I was talking about in case of effort gravity. But if you look into the second term, it gives you a Yukawa correction, e to the power minus m psi r, where m psi is the mass of the scalaron field, which we call scalaron degree of freedom. And this is known as scalaron fifth force. That is, I used the term fifth force in my paper, in the next paper, that I was trying to use effort gravity to test near-nickel epicenter black hole. Now let us see whether they can affect the pericenter shift of the compact stellar orbits near the black hole. This is the GR plot like before, but this time I have plotted with semi-major axis starting from around 50 AU to 1000 AU towards the orbit of SO2. Eccentricity is the parameters because the stars have different eccentricities starting from 0.1 to 0.9, and the y-axis is the pericenter angle, rate of pericenter shift in general relativity, and these three graphs are for FR gravity. So we see that if we have low mass scalaron like 10 to the power minus 21 electron volt, then the FR gravity effect builds up towards the larger orbital radii. But if we go to higher masses, something like 10 to the power minus 20 or maybe minus 29, minus 17, minus 18 electron volt or something, but this I have shown a graph for 10 to the power minus 20 electron volt, then we see that this scalaron effect is building up towards the compact stellar orbits. So we have two regimes near the galactic center black hole. If the scalaron is light enough, they will be screening, they will be unscreened towards the larger orbit, and if the scalaron is massive enough, it will be screened in the larger scale, but it will show its effect in the compact orbits. And that was what Dabojit was speaking in the last talk, that there are scalarons which are hidden in the compact space-time regime. If we go to 10 to the power minus 16 electron volt, this is the prediction based on quantum correction of Einstein's equation near the black hole that I did in 2020. Is the most massive scalaron that we can have. Then we can see that there is no effect of this scalaron beyond 20 AU near the black hole. If there is any effect, it has to be below 20 AU. That means the massive scalarons are screened, much screened, and it shows the effect towards the compact stellar orbits. This is the paper that I was talking about, scalaron fifth force, that was in APJ. One of the results is a focused object paper. If we see the conclusion of my paper, this is a new window for massive scalarons greater than 10 to the power minus 20 electron volt. And from the calculation, it is seen that if we concentrate in a semi-major axis to 100 AU and eccentricity 0.5, for example, then the pericenter shift in FR gravity is something like 50% of the GR. Then if we go to eccentricity 9.9, very high eccentricity orbit, for the same orbit like 200 AU, then we find that this pericenter shift due to scalaron fifth force is something like 1% of the ZR value. It's quite small. Therefore, if we take the ZR value something like 1000 arc-second per year, that is from the calculation, then we find that the scalaron effect is something like 10 arc-second per year. The pericenter shift will be contributed something like 10 arc-second per year. Now if we see that whether it is measurable or not, then we come to the astrometric accuracy of the telescopes. Existing astrometric accuracy is the gravity detector. It's an interferometer in VLT. That detector has astrometric accuracy of 10 to 30 micro arc-second. And when the ELTs will come out, they will have astrometric accuracy something like 5 to 10 micro arc-second. So we have a good hope that we can constrain these scalarons, or we can rule out this scalaron by having the ELTs that is upcoming. Now let's see whether you can find breaking point of GR not through scalarons but through higher dimensions. And I have taken in my work the prototype higher dimension, the classic theory of Kaluza-Klein. If we have Kaluza-Klein gravity, then it is expected that we have the 5-dimensional Kaluza-Klein particles. And it is proposed by many workers that higher dimensional particles can act as a non-baryonic dark matter. But this is quite deep theory in cosmology, that how higher dimensional particles or higher dimensional degrees of freedom can act as candidate of dark matter. That has not yet been testable in cosmology, but we can use the galactic center black hole to give a lot of constraints on that kind of models. And the 5-dimensional Newtonian potential, if we take Kaluza-Klein gravity, then the Newtonian potential gets modified like 1 by r square. It is not 1 by r. It is 1 by r in Newton, normal gr, 1 by r square for Kaluza-Klein gravity. And it is parameterized by something called 5-dimensional Planck mass, which is related to 4-dimensional Planck mass through some parameter called c. And this is the result that we got out which my first PhD student, she did the calculation that how it can affect the pericenter shift. And if you see the diagram, the solid curve is Schwarzschild pericenter shift, the dotted curve is the power law pericenter shift. Power law is P equal to 1 by r square, Kaluza-Klein gravity. Now if I choose the 5-dimensional Planck mass, which we call as a Kaluza-Klein particle, something like 10 to the power 3 ZeV or 10 to the power 4 ZeV. Why 10 to the power 3? Because 10 to the power 3 ZeV is the supersymmetry breaking scale, and we want to see that if the Planck mass or the Kaluza-Klein particle is above supersymmetry breaking scale, what should happen? Because below supersymmetry breaking scale, the physics is understood. The LHC physics and other particle physics model is well understood. There is no such effect called Kaluza-Klein. If there is any effect of higher dimension, it has to be above the supersymmetry breaking scale. That's why we have got above the supersymmetry breaking scale, and we find that if it is 10 to the power 3 to 4 ZeV, then the power law of gravity dominates over the pericenter shift, and that is the breaking point. It is testable now if it is within supersymmetry breaking scale. If Kaluza-Klein particle exists or the higher dimension exists, then it will be automatically ruled out by the upcoming observations because it is above the Schwarzschild pericenter shift. Now if we go back to higher masses of the Kaluza-Klein particle, something like 10 to the power 5 to 1 million GeV, then you find that the effect of higher dimension is suppressed by the general relativity effect. These two graphs are showing about. So that says that this model can be easily ruled out. If we go from say 50 AU to around 1000 AU, within that region near the black hole, the Kaluza-Klein particle can be easily constrained. So this is another potential of the black hole. This is the paper, and my first PhD students he submitted the thesis. Is it possible to see the breaking point of GR? Consideration from scalaron and higher dimensional gravity as well. We had some comparative work, comparative study with scalarons, but I am not showing the comparison here. And you can see this, all these scalarons in the range 10 to the power minus 22, minus 17, and the potential 1 by r square. It has been taken together and tried to see whether we can detect the breaking point of GR near the black hole. Now my last point is whether we can use the shadow diameter of the black hole to test gravity or to understand gravity. This is EHT's result, April 7, 2017. This is our black hole, Sagittarius A star. The size of this shadow is 50 micro arc second, something like 10 times the angular diameter of the event horizon. So all we have to calculate is the photon ring. The photon ring is the, how do we get a photon ring? Because the light is bent by gravity, and if we have an impact parameter less than a critical value, the photon will be plunging to the black hole. So that defines what a photon ring is. And the expression of the photon ring is dependent purely on the metric, ZTT, the time component of the metric in space-time. So this is a pure metric effect. If we don't consider the plasma effect going on near the black hole and consider only on the shadow part, the brightness depression, it is a purely metric effect. And the diameter of the black hole is purely governed by the photon ring and the ZTT, magnitude of the metric in the space-time line element. And the major diameter that EHT reported is 48.7 plus minus 7 micro arc seconds. So we can use the measured size of the shadow to say something about the metric. And I have chosen few metric. This work has been done with one research intern from VIIT Ranchi. She came to have some internship with me last year, and she worked for 1 month, and we realized some interesting results, and some communication has been done with European Physics Journal C, and that is sent after some minor revision, and we could give some strings and bounds on certain parameters of metrics both within general relativity as well as outside general relativity. So the first metric that I shows the Reiner-Nordstrom metric with a tidal charge. This is not elliptical charge. This is a tidal charge because Reiner-Nordstrom metric is ruled out because black holes cannot be charged, elliptically charged. So, but in higher dimensions, tidal charge can appear as an extra degree of freedom. That is what Q square by M square. M is the 2gm by c square, that gravitational range. So we see this that if we plot the shadow diameter with tidal charge, we can give constraint. This box, this shaded box, is the allowed region of the tidal charge, which I have displayed here. It is lying from minus 0.57934 up to 0.86. But if we go back to the earlier result of the shadow diameter, the M87 bound, it was reported by Zakharov 2022. The tidal charge is lying between minus 1.22 and 0.814. So our result is much more stringent compared to the M87 bound. That means the Sagittarius A black hole has given a stringent bound on the tidal charge if it exists. So that is a realization, and we had given certain comments on higher dimensions and its relation to tidal charge by this particular constraint. Next is Kerr de Sitter metric. The astrophysical black holes are Kerr black holes, but if we have a dark energy background or in a de Sitter background, then we have to consider the black hole embedded in a de Sitter background. So again, we have plotted this shadow diameter versus cosmological constant that appears in the metric, Kerr de Sitter metric. And again, this rectangular shaded box is the allowed region of the cosmological constant. So if we see the bound for spin 0.1 and spin 0.5, because that is what EST is demanding, the black hole is a low spin black hole, it can lie between 0.1 and 0.5, Kerr parameter I am talking about. And when we find that the cosmological constant bound, that is 10 to the power minus 40 centimeter inverse square, and lies the upper limit is 10 to the power minus 25 centimeter inverse square, that is hard calculation. But one surprising thing is, this bound that has been found for the Kerr de Sitter metric is something like 16 to 31 order magnitude higher than the cosmological bound, because the cosmological measurements of the lambda parameter, which may be candidate of dark energy, has been found to be 10 power minus 56 centimeter inverse square. So we are trying to understand why this lambda term is too big if we calculate, if we give bound near a particular black hole. So one of the conclusion can be maybe the cosmological constant that appears in black hole physics is something different from the lambda term that Einstein proposed, or maybe the dark energy candidate. So we have to disentangle these two things. Then I come back to scaleron, whether the shadow can give some bound on this scaleron. If we again study this shadow diameter versus scaleron mass, then this rectangular box is telling me what is the allowed range of this scaleron mass. And we find quite stringent bound relative to our own work that was published in 2020 and in 2022, from minus 10 to the power minus 22 to 10 to the power minus 16 electron volt. That was quite wide bound. But here from the shadow we get 10 to the power minus 17 to 10 to the power minus 16 electron volt. This is a very stringent bound that we can give on scaleron mass from the shadow diameter. That means that if there are scalerons, for scalerons, they have to be extremely massive. And that is in the safe side, because if the scaleron mass is quite large, the Yukawa term become quite less in large scale. And we are safe to say that gravity acts like apple falling, okay? Because Yukawa will be absent. But if we go to the smaller scale, that higher mass scaleron will show the effect because of the screening, a particular screening effect. So this work that Pranjali, Dr. and all these things, she did it within 1 month, and she wrote the internship report and sent the paper. And this is after a minor revision. We are planning to send to European Physical Journal C, and this was some realization from the shadow part. Now I will conclude. The galactic center black hole is an eligible lab to do all these that I have displayed. We can constrain geometrical alternatives to ZR, I mean the upper theories. We can constrain higher dimensional candidates of dark matter, I mean the Kaluza-Klein particles we can constrain. Then we can also constrain parameters of matrix within and outside GR. And the next thing that I am looking forward, we can have a lot of constraint on other modified theories of gravity in that wide scale starting from the shadow diameter 0.4 AU up to the SO2's orbit, which is 1000 AU. So this is a good laboratory with which we can try to understand how gravity works, how space-time behaves, at least in the classical domain. Thank you very much. I think it was revealed to you. This I took from internet yesterday. Enjoy your moments in the coming hours. And this is a picture I took from my mobile, Sri Govindaji temple. Thanks to Ablu, he took us to that temple. Very peaceful place. Rejoice your moments. Thank you.
Okay, thank you, Dr. Sanjeev, for your nice presentation. It is now open for discussion. So, any question?
I have a one.
Yeah.
So you talked about brain Dickey's parameters. So is there any upper bound for that?
That omega parameter you are talking. Solar system says it is something like 50,000. The Mercury is perihelion shift. That has given very strong bound on omega parameter, that is 50,000. And in my plot I have shown 40,000. But if you go down, that will be maximal deviation. So even if we go to 50 or 100, which is quite small, but the deviation is large, then also the difference between branch decay and GR in the pericenter shift of those stars is something like 1 microarc per year. So I have doubt whether the ELTs will be able to do that. That's a good thing because in the solar system we do not distinguish between branch decay and solar GR. The galactic center also telling the same story that if the modified theory is branch decay, then you cannot do anything. You cannot disentangle from GR. That's why we move to FR, which is more general than branch decay theory.
Is there any more question? So, I have one question. So, regarding your tidal charge, is it gravitational in origin?
Gravitation?
Gravitational in origin? Tidal charge. What is the origin of tidal charge?
Yeah, it is gravitational origin but higher dimension.
Okay. Is it bipolar?
No, it is not bipolar. It's a degree of freedom.
Okay, fine.
It's a degree of freedom, and some people say it should be some kind of spin zero particle. I mean scalar field. But as yesterday you were talking about scalar charge.
Yes.
So some people are expecting that it should be some spin zero field. That's tidal charge. But that was proposed in 2005 by Dickey from IUCAA, that tidal charge should be present because of the higher dimensions. But we're trying to correlate with spin zero field or scalar field if it is possible.
Okay.
By nature it is gravitational origin.
Okay. So, regarding another, your gravitational journey, so your Eddington inspired born-in-field gravity was missing.
Yeah.
I didn't see anywhere. So, why you didn't mention anything? That is also regarding your GR connection.
Yeah, I have not tested it, but born-in-field theory people are using in dark energy physics recently for understanding the acceleration. Yeah, as Deposit told yesterday, that we have plethora of or a spectrum of modified theories of gravity which we can test in near future. But again, if we are doing phenomenology, so we have to be careful whether it is testable by the upcoming ELTs. So we will try to constrain those theories as much as possible.
Okay. So, last question. Yeah. What are the extreme scales for which escalation effects are going to be realizable? Somewhere you have shown the mass of escalation is your 10 to the minus 20 eV.
Yeah.
So, it is very small.
I think
Okay.
In that paper I mentioned, possibly in the 2020 paper.
But it is variable, not fixed. So, I want to know the extreme scales.
Yeah, I will show you the. No, not this paper. This is.
They are minus 21,
This,
minus 20.
if you see the sentence, it is found that scalarons resulting from quantum fluctuation effect, the precession of orbits with A equal to 128 to 56 RS. RS means gravitational radius. This is the scale.
Okay. Okay, thank you, Dr. Sanjeev,
Thank you.
for nice presentation. So let us give a big hand. Okay.
I'm thankful to Manipur University for giving me this opportunity, not only for the talk, but we are enjoying, as Himadri said, we are enjoying the place, we are enjoying the weather. It's a nice thing and a nice place. People are nice, and we are looking forward to visit once more to Manipur University. Once, maybe twice, or maybe a number of times. Thank you. Thank you.
Okay.